All right. So let's start maybe. It's I first thing that I would like to say that my name is Przemyslaw Maziarka and I'm going to be extremely brief. So all the detailed information you can ask me in the question phase or then afterwards after the presentation. The topic of my presentation is a prediction accuracy in the modeling beechwood pyrolysis at different temperatures using a comprehensive CFD-based single particle pyrolysis model. It's quite a lengthy title. So yeah, let's go to the details of it. First, maybe I will highlight my role in the GreenCarbon project. My role in the project was development of a comprehensive pyrolysis carbonization model to predict the properties of co-produced biomass-derived carbon and bio-oil, where it's located within the GreenCarbon project framework, just in the middle, in the optimizing process conditions to produce tailor-made biochars and linking biochars with the feedstock properties. Let's go back to the subject of the presentation. We all know that the biochars can be applied in the variety of the novel solutions, like in the agriculture, chemistry, electronics, in the batteries, supercapacitors. There is some research on those applications, but the question is like why we don't use biochar on the large scale in those applications yet. It seems relatively simple to produce. We start from the biomass and we pyrolyze it in a certain temperature, and we obtain the biochar. Yes, but the problem in here is that those biochars do not have tailor-made properties, so they are not made specifically for each application. The properties of the biochar is sometimes completely random. That hinders from their application on a larger scale in those novel applications. Where are the problems located with the production? The first is the inhomogeneity of the initial factors, so inhomogeneity of the biomass. The biomass has strong deviation in its properties, and also we don't know all about the process that it happens during the production. In the chemical point of view, so in the reaction kinetics, there maybe we know a lot, but in the case of the production of the material, there is some other properties that needs to be as well taken into the account. And changes, especially changes in the porous structure, is not known yet. So we have some lack of knowledge, which really hinders us from production of the tailor-made biochars. Since we have a lack of knowledge, the very intuitive way is to conduct the research and bridge the gap. But the problem here can be that this only experimental way can be quite expensive. It requires a lot of manpower and it's time consuming. Yeah? But there is also an option to couple the experimental work with the modeling work in order to reduce in theory, to reduce the time and reduce the cost to bridge the gap. And on coupling the experimental and modeling work, this is more or less the subject of this presentation. So I will start maybe from the explanation how the model was developed. So the model preparation with external data. First, I will say a few words about the influence of the wood anisotropy. Then a few words on the selection of the most appropriate kinetic scheme of the biomass degradation, and then the validation of the model against a broad range of the parameters, the particle size and the pyrolysis temperature. Then I will focus a bit on the experimental work that was conducted, so the single particle pyrolysis of the wood cylinders. So in here I will explain the range of the research that was conducted, and we're gonna briefly go through the overview of the results. And the third most important part, so the validation of the previously established model with experimentally obtained data. And here we're gonna check the prediction of the accuracy of the center temperature and the mass loss profile and the yields. And based on that, some further improvements will be indicated. So let's start from the model preparation with the external experimental data. So in brief, the CFD model is a numerical based model, so it's built on the only on the mathematical equations. The most important ones are the governing equations, which drives the physics of the whole process. Also, the auxiliary equations needs to be implemented. So the equations that have some experimental or theoretical foundations, and also the boundary conditions needs to be well established, because they are the drivers of the changes in the process. Each specific models have to have very detailedly implemented parameters. There is plenty of different parameters that needs to be implemented to the model prior to the simulation. And the most important things in here that chemical and thermophysical parameters relations and have to be directly correspond to the modeled scenario. So for each simulation, for each model, parameters have to be metrically very detailedly checked if they are correspond to the situation that's want to be simulated. Okay, so the first study was focused on how relevant is the wood anisotropy in the model. These are the specific parameters that have been used. In general, all the numerical investigation was made on the principle that the model changed only in one part, just to compare how that part influence the outcome of different scenarios. The second study was the investigation of the kinetics, so which kinetic scheme is the most important one, the most accurate one for the large particle pyrolysis, and the third one was the validation over the broad range of the parameters. As you can see that the number of the parameters increases with each step. So let's start from the wood anisotropy. As we all know, the wood have different properties in different direction. There are three different directions in the wood structure: radial, tangential, and longitudinal. This is related with the fiber direction of the wood and also of in the lumens. The two parameters that are the most dependent on the direction are thermal conductivity and the permeability. Experimental data indicates that in longitudinal direction, those parameters have totally different values than in the radial and tangential, but between those two directions, radial and tangential, there is not a lot of difference. That really indicates that model can be reduced from the 3D to 2D because only two dimensions are really different between each other. This study had to prove that the 2D is the really lowest dimension, lowest number of dimension that can be used. So there was two investigated scenarios, anisotropic and isotropic. Anisotropic thermal conductivity and the permeability was different in longitudinal and the radial direction. And in isotropic model, those parameters were average and they were same for each direction. And in here, it was like if the isotropic model would be as accurate as anisotropic model, then we will not really need to implement the 2D models and we can only focus on the one-dimensional models. But the question is it really true? So the first comparison of the temperature profiles and the mass loss profiles indicate that averaging of the thermal conductivity values leads to the strong overprediction of the temperature of the center and also overprediction of the conversion speeds. So the isotropic model is not really accurate in comparison to anisotropic model. That means that the thermal conductivity directional dependence is very relevant for the model. The other thing is there was an investigation on the intrinsic gas velocity distribution. And as it can be seen on the right-hand side, that if the model have isotropic properties, the gas takes the shortest route to escape the particles. In that case, the radial direction, which is not really a realistic distribution because in longitudinal direction permeability is much lower. So most of the gases are released on the escape through the longitudinal path, and this explicitly doesn't have the much influence on the thermal behavior of the particle, but it has very strong relation to the secondary reactions that can occur within the particle, because it's very relevant for the residence times of the vapors within the particle. So long story short, the anisotropy have to be implemented in the models, and the 2 dimensions are the lowest number of dimensions that needs to be implemented. Let's go to the investigation of the different kinetics. We start from the very simple kinetics, where the biomass is implemented as a bulk compound. There are 3 products. This is the Zavidech and Chin's reaction scheme. 3 reactions for compounds, very simple. We also check the different degradation kinetics, the most detailed one, in which biomass is in the form of the component mix. And there are numerous products, volatile products, and char, which is modeled as a pure carbon, and metaphase traps, which degradation mimics the devolatilization of the carbon during the process. We select here 2 models, Ranzi and Ranzi and Anka Koche, if I pronounce it right, RAC model. The first model was developed mostly to predict the fast pyrolysis, and the second is the adjustment of the Ranzi model through the 4 parameters of the secondary charring, which should then the model should be more accurate in the prediction in other than kinetic thermal conversions. So let's check the results. Firstly, let's compare the simple and the detailed models. Can be observed that simple model doesn't really predict the temperature profile quite well in comparison to other to the detailed models. Also, in terms of the lump product yields, it's not the most accurate one. Also, it doesn't really predict the detailed release profiles of the compounds. Then the comparison between Ranzi and RAC model indicates that Ranzi model doesn't really predict well for the same property.
Rapid. 1 minute left.
5 minutes? Okay. Okay. In general, this investigation leads to the point that RAC model should be implemented because it's the most accurate one. Then the model, there was the model prepared on a broad range of the parameters, so 4 temperatures and 3 particle size, in total 12 different scenarios. And due to that, the scenarios really changed. The secondary charring parameters were implemented as a functions, depending on each scenarios. As can be observed that temperature center and the mass loss profiles were quite well predicted in that case. As can be seen that for the mass loss, the lower temperature doesn't really, it underpredicts the char yields in that case. And for the temperature center, in temperatures above more or less 600 degrees, there is in the initial stage on the conversion, there is some deviation between experimental and model data. Okay, so let's go to the experimental part. In that part, some single particle pyrolysis were conducted in 5 different temperatures. Each experimental point were measured 6 times, 3 times with the assessment of the release of the compounds online, and 3 times more to collect the heavy vapors. This is more or less how the reactors, the scheme of the reactors look like. And in this, in the reactor, can be measured in the real time temperature center, surface, mass loss, and release of the compounds with the 2 different detectors, in the TCD carbon dioxide and carbon monoxide. And in the FTIR, those 2 and 13 other more of the light compounds. For the secondary analysis, samples were collected to expand the model to make some additional measurements than the direct real-time one. So the char samples and heavy condensables were collected as well during the experimental work. This is more or less how the reactor works. And here, this is the sample. So you can see the difference in the sizes in here. This is how the sample looks like before the process. In the center point there is thermocouple inside to measure the center temperature. This is how the process samples look like.
Przemy, we are 50 minutes now, so go directly to the conclusions, please.
Directly to the conclusions. Okay, so directly to the conclusions, and here on the way there is that the models fit the experimental data, but maybe not at the 300 degrees. And the mass loss it's not that accurate, but it needs to be adjusted. In terms of the yields, when the secondary gas phase reactions occurs, the model loses its precision in the yields prediction. So that means that secondary reactions need to be implemented, but for this, not only particle but also surroundings have to be modeled, and to be more precise, when the temperature distribution shrinking have to be implemented. And currently in the software that is used, it's not very straightforward how to do that, but the data, experimental data on those is already available. So to sum it up, the model, the established model was valid for a broad range of the parameters. The experimental data set was kind of broad, and there wasn't really a strong deviation in the experimental results. Currently, the model shows satisfactory fit to the experimental data, but still it needs to be slightly adjusted to obtain required accuracy. And the most important thing that it has to be expanded to predict the pore size distribution. The porosity, the porous structure of the biochars. These are the publications that are relevant to the subject. And thank you for your attention.
Thank you, Przemy. Okay.
Sorry, as I mentioned on the beginning, it was extremely on the surface. There is plenty things that I can be focused on, but I would rather to give overview of the scope than focus on some details.
Thank you, Przemy. We have time for one question. Gianluca, can you see it? Yes. I see. Can you see the question, Przemy?
No, I don't see really. I have to. I'm not really sure how I should minimize it. Can you just?
Thanks very much for the interesting presentation. I think your study might be really helpful to understand how to reduce the variability in final properties of biochars. My question is this study applicable to the industrial reality?
Yes and no. The problem in here is to firstly establish the conversion of the particle in very detailed manner, just to assess how the particles changes, how the properties change. And then when that will be like very detailedly established, the model can be simplified. So we can decouple the governing equations from the outcome and have some simple mathematical correlations that can be further transmit to the higher level of the modeling in that way. In general, this kind of research gives base information about the changes. So based on those numerical research, some experimental works can be driven in the different directions, which can be also connected with the industrial approach.
Okay, thank you, Przemy. So we can.
You're welcome.
Bye.
Thank you very much. Thank you very much for having me.